I'm sorry. Let me say the story again. So the story is the following. What we are learning so far in 3300 is what? We started syntax, right? Okay, we know some syntax. Syntax is not the language. Also, we know, oh, in 2300, we know there is something called decoder. Oh, we have no, we figure out there's something called encoder. We figure out something is called multiplexers. We figure out some is called gates and truth table and so on. But, here we should have more. The outcome of the course is the what? Integration. So you write syntax and you integrate. Do you remember in the 2300, you go to build the decoder in the lab, right? So you bring this little itty bitty chip and you put it in the breadboard and you start communicating with 7-segment display, and you have the decoder of the 7-segment display. You connect the switches in the breadboard with a bunch of wires, and then voila, it works. So what you did in the lab actually is called integration. That makes sense? Because you start integrating pieces on the breadboard. Now on 3300, you're integrating also, but you're integrating in what? Software level. And everything will be inside the chip. Not multiple chips out and you are trying to communicate between them. I just want you, every time you feel it's confusing, you turn it back to the old story. Why we are learning 3300. Yeah, besides getting the grade and you move forward with the requirements, stuff like that, that's fine. But why we are bothering ourselves and learning 3300? Because we figure out it's limited to use breadboard. It's time consuming to have a jungle of wires, and one of them is loose, and then you have to collapse everything and build everything from scratch. That makes sense? Then we start moving into the software level. Then oh, software level looks really cool, but it has some problems. How are we gonna deal with these problems one by one? This lab, the target of the lab, it was integration. I know integration is not easy. And also I didn't give you every single step. So for instance, a couple of people came to me and asked, what next after, the memory? So what next after the memory, it's a kind of knowledge we know from the 2300, there's something that's called parallel input, serial output. So there is something in the circuit, it's called serializer, deserializer. Have you guys heard about this concept before? Somebody telling you serializer. What does it mean, serializer?
It took the 32-bit input and then it outputs 1 bit at a time.
Exactly. So that what does it mean if you match it with 2300? PISO, parallel input, serial output. That makes sense? Then there is more we can add into it, right? So why we should have the memory? Why we don't even use FIFO? So we can make a streaming. Why we have to wait until the memory will be filled with data, and then we're gonna in serial, right? You understand what I'm saying? Because every single word in the experiment we have is 4-bit. Do you guys agree? So 4-bit, I can actually, while I'm actually breaking the first row into bit, I can actually fill the second and the third and the fourth location with 4 bits. Do you guys agree? 4-bit. So actually the filling rate will be faster than, consuming rate. So, putting data into the FIFO would be slower. So maybe we will need, in that case, something is called clock domain, or, multi-clock domain. Because, the feeder, not the feeder, the one is actually shuffling data and storing data is not fast as it's faster than the feeder. Right? You understand what I'm saying? Or should I draw it?
I think that makes sense.
The rest of the nation, you guys understand what I'm saying? Or should I draw it in front of you? I can draw it, that's fine.
I would like a drawing, yeah.
I love drawing, I know I draw ugly stuff, but what should I do? Circuits you have to draw, right? So one.
So that PISO is only after you have achieved that 32-bit.
Yeah, not even 32. You can actually play more than 32, right? I will show you some tricks. That's why, you know, we are also here for designing. So when you say design, that means I give you what? I give you more space, not more guidance. You understand what I'm saying? Because you are a designer. One second. What? I need my password. I didn't even know what is my password. I never use password for this. 1, 3, 1, 8, 8. Seems that they made the changes in the what's called in the Zoom. And even, you know, I have to allow myself to be in. That's ridiculous. Then I go here, share screen. So I have to make myself co-host. Oh my gosh. Okay. Screen. Okay, now is my notability. So it's 300. Okay. So back to the point. Imagine the following, right? Imagine that, you know, we have a person here, right? And we have here the restaurant, right? And this guy is very hungry. Okay. And, you know, here's the waitress, whatever, right? So this guy is moving the food to this guy, right? Sounds good? Imagine that, you know, the time this guy is taking to eat the plate that, you know, the waitress already give it to him, place it in front of him, is actually shorter than the time that guy actually taken for preparing the food. What will happen as a consequence?
You'll be waiting longer.
He will be idle. He will be mad. He will be like, you know, I'm still hungry, right? So in that case, we need what? We need a mechanism making this guy to be faster than this guy. Or stuffing stuff for him, like putting too much stuff. So in this case, we can do something like that, right? Align, the waitress will just keep pushing. So the speed the guy is taking to fill the stack, it should be faster than the way that, you know, this guy will be picking food out, right? And this is what? FIFO. So if we have a FIFO, this FIFO can be working in two what? Clock domain. One domain will be sure that, you know, the FIFO will never be empty. And one domain will be actually taking this into another level. And what is another level? So here's the thing. When I said use memory, I showed you last time that, you know, you can actually use normal memory like the one I made with finite state machine wrapper. And from there, you can actually read and write. You guys agree? So that's actually the one you should use in that case if you are looking for streaming. So back to the experiment itself. Think about it from a different perspective. Here's the thing. You know, I can make it in a very easy, safe way. I have a table. I know that every single row here is 4-bit. How many of those rows do we have? We have 8. I don't remember 8, right? Then, you know, what I can do, I can start doing like this. I can make here like a pointer or address pointers or address bus. And I said, yeah, you know, point the first data of the switches here. Then I increment 1. The second will go there. Then I increment. The third will go there. Then I increment. The fourth will go there. I have 4 locations, right? I'm done. So the time that, you know, I found my pointer here is tend to be 3. It will automatically be enabling the process of kicking out. That makes sense? If you are looking for one cycle system, that means system will just run one time. Then I will start taking. So, you know, I see 3 here, right? So the next cycle, you know, the address here, it would be 0. Then, you know, I know on this bus, there is 4 bits here. 1, 2, 3, 4. right? So those 4 are already on this bus. So that bus, it has to be what? It has to be PISO. Do you guys agree? So in that case, I can look at it as the following. I can just make it, you know what, make it more entertaining. So I can make it like this here. I place here 4 locations, right? Then you know what I'm expecting? I'm expecting the output to be like this, serial. Then you know I will have a counter counting here. I 1, 2, 3, 4. So it's 4 location, right? Like this. Count 0. I'm pushing by 0. I found here, the first bit came out, B0. Then B0 will be pushed in directly to who? To be pushed to who? To the sequence detector. What's it going on here? Sequence detector, right? Then count 1. B1 will be the one is taken over. Count 2, B2. Count 3, B3. Right? Then what will happen? I stop, right? Then the time I will go in a count 0 again. What will be happening? This guy will not be longer 0, it will be 1. So that means the second word. Then I will do this over and over and over and over. And of course, I'm feeding the sequence detector. That does make sense? But of course, this is not a very great solution, but it's a solution, right? The second possible solution is more crazy, which is like FIFO. And I will keep pushing here 4 at a time. Then I will have here here basically I push here I pop, here I push, or I can call it pull. I pull out data. Then I have here still 4 bits, right? So I will also push. I will see my flag here. I will have a finite state machine. It will check. It will check what? It will check the empty flag and full. So if it's empty, I will do nothing. If it's full, I do work. If empty is not high anymore, that means there is data. Do you guys agree? That's a finite state machine. So I will see, oh, empty is not high anymore. So there is data. Then I will do what? Full is not important. Full will be here. I will tell you what. Anyway, so when it's not empty, what I'm gonna do, I will pull 1 time, and I will have a counter counting 4 times. Why 4 times? So the data will go here, and I start breaking it to B0 cycle, second cycle B1, B2, B3, right? Then once that counter will be done, it will pull 1 more time. So every 4th cycle, there is a cycle pull. And when you say empty is over, you stop. Then the second guy who's pushing, I'm pushing, but when I see full, I don't push until full will go down. When full go down, that means I can push. That means there is a space. It will be happy to place the new taking the new segment of data. By this way, you are building a kind of a streaming mechanism for feeding it's like a feeder, feeding what's called the sequence detector. And of course, the output of the sequence detector will be the switch of the enable. Do you guys remember that one? Will be enabling the up-down counters that we were talking about. So does make sense?
The counter for the PISO, that's what that second half of the drawing is, right? The PSIO.
Yeah.
That counter is for the index of the word.
Yeah, it's indexing words. Yes, correct. So it's pretty much is like indexing. So you already have here the word is B0, B1, B2, B3.
Okay, and through that way, we were able to feed the sequence detector word by word instead of trying to create a 32-bit value. There's no need for a 32-bit value.
Yeah, I mean,
you just go by.
Yeah, you don't need even a register like Rohit was talking about. You just need like a wire. It's a wire with counter. So basically what you can say, let's say the output of this detector of this guy is called Z, right? So basically you can make a case statement if you want. I mean, there's a ton of ways you can do it. Like case statement saying that, count 0, right? Z equal B0. I'm not writing in Verilog now, I'm just writing in a concept. Anyway, count 1, Z is B1, count 2, Z is B2. Somebody will tell me what is B0. Let's say this bus is called B, right? So I can just remove this and say B like this, and in location 0. B like this, location 1. B like this, location like this, and so on. That makes sense? So you need a sequential behavior here. Mm-hmm. Why sequential? Because you cannot make it like a maximum. There is a different way you do it if you would like to build the structure. So here is the structure. It's more fun, Look, you already have here, let's say this is the bus, right? And this bus is called B, and this is 4-bit, right? What I can make it, I can just say that, B0, B1, B2, B3, and then I put multiplexer. Do you guys agree? That's a combinational circuit. 0, 1, 2, 3, and Z. Then, this controller is 3-bit. They're going to be a counter. Make sense?
Would it be wrong to parallelly try to copy the arrays that are the words onto to take those 8 arrays and insert them into a 32-bit simultaneously through the GEN bar generator?
There is another. I mean, I'm giving you multiple ways. I'm not restricting, but the one I said 32-bit, 32. Just make a big one, 32, and you just wait until the whole 32 will be ready, and you stick it one by one. That's one of the possible easy ways. Mm-hmm. That makes sense. I mean, but multiplexer is more reliable. The system is actually multiplexer with a counter, so it's a 3 flip-flops and combinational circuit of multiplexers. So when you say 3 flip-flops, so when you go into the resources counting, you will just find 3 flip-flop, literally 3 flip-flop. And then let's see those multiplexers. 4 is basically 2x, right? 2 multiplexer, 2x1. So that means maybe 2 lookup table, 2 lookup table, 3 lookup table.
For the address pointer for the read of the memory, would that be controlled by the switches, or do you just have that cycling?
I would say automated would be better, right? Because once you fill, you don't need to touch by hand, right? Mm-hmm. I mean, I'm not saying anything wrong about if you make it manually, but what is the best for you to do? My question. Do you prefer it to be manually, or do you prefer it to be automated?
Very well, should be automated. Yeah.
Should be automated, right? Because at the end of the day, the only thing that you are responsible for is just for switching. Right? Your system is smart. It will fill data and stop. It will digest it. Then it will ask you, I'm hungry, give me more. And that's why I give you the UART, if you remember. Because you can do it easy in the software.
So there is no load button then for that. So as soon as the memory is full, it will automatically begin.
Exactly. You will see a flag here, full. I'm full. Yeah. Don't take. I'm not full. Keep pushing. Maybe we can make also fancy thing. Like most of the movies when they say the end. Once you are done with the data, you need to send message say that I'm done. And then it will close all the communication protocols and everything, and say shut down the door. Everybody's going to sleep. I mean, like example like that. You know what I mean? So you will decrease the amount of power consumed, because don't forget, when you establish communication between 2 devices, that's actually power, right? So when you keep the channel live, that means you are actually consuming power with even it's a terminal power. Make sense? Hello.
Yes, Professor.
Yes. So anyway, in general, what I want to say, the idea of this lab is system, because don't forget, whatever assignment we agreed about for the project, it looks system to me. You know what I mean? That makes sense. And it would be awesome if I see you guys have a very, I mean, I'm not gonna say expert, but since it's a 3300, so at least a level of understanding systems and how can you integrate pieces together. That will be over time. When you will go in a 4000 level, you take like 4305 or other like computer architectures, all of these things, you will be mature enough to move forward to the high level than struggling to understand the high level from the beginning. You know what I mean? Okay, anyway, I don't want to waste your time. So basically, we agreed about that, you guys gonna show me what you already have done so far, right? And also I'm gonna describe to you how the VGA work or so, right? But also I have something else to share with you. We are in week 13. So maybe I can add extra little bit thing, which is basically it's called PWM, pulse width modulation. Because we don't, we still have week 14s, 15s. I will let you focus more with your work and presentation, but week 14s, we still have time, so I will give you the VGA with more fun. But I can share with you something about VGA, but then we will move to the PWM, then I will turn it back to VGA later. Okay? Before I move to VGA or PWM or anything, UART was clear to you guys last time? From the last time, I'm sorry? Huh? That's very nice to hear. So let me see, where are they? Because as I told you, we are not inventing a new material, because everything exists even before even I was exist. So I can give you a research for other stuff, but that will be too much for level of the undergrad. So I do crazy research, other stuff. Here, can you see, guys, the screen in front of you?
Yes, Professor.
Okay, so to understand VGA or any different serial communication protocol, you have to put in your mind two things. Okay, physical and what logical level. So what is the definition of engineer? Engineer is a person who can interpretate between the physical meaning and the mathematical meaning of a certain phenomenon, right? So we are not mathematicians. We are not working physics. So basically, we are something in the middle. You know what I mean? We are taking the physics and we are taking the math, combine them together, we build product. This product will help society. Help it in the civil, help it in the industry, help it in the military, space, whatever. Healthcare, something. If you look to one in front of you, this is more into what that's fine. That's fine. So maybe the news. Did you get the email from what's his name, Professor Hussein?
I did. Yes, I did.
Yes. And he sent me email, and I think everything looks fine. Okay.
Okay, perfect. Thank you.
No worries. Anyway, so back to the point. So if you look to the VGA, it's a part physical, which is people who build the physics, like build the circuit from the physics perspective, and also building the driver from the software perspective. So if I look to the screen, that doesn't give me any information about the physics. That does give me information about the firmware, which is a job that people actually looking for. And I believe you guys would be a very good candidate for working on this after you graduate. So look at this. What is this in front of you? What does this mean for you? This is basically the screen. So the screen we are using at the moment, the screen I'm talking now and I'm looking at it, it looked like that. A hidden area, which is, do you see my what's called the cursor?
Yes.
So did you see this area? This area is empty. This area is nothing. This area is basically black. I mean, you cannot see anything. It's dark. So where is exactly the screen we can see? This one. This is the display time. So pretty much, the people who work on building VGA, I believe it was IBM. So, I mean, if we look here into the Wikipedia, it's not written by me, VGA Wiki. So VGA, it was made by who? IBM. At the time that, people were looking for what? Looking for moving from this, the tube TVs and tube screens, moving into this flat screens. And now they have this folding screens, and they have all of this craziness of LED and LCDs and, all of this fancy and touch screens and all of this perspective stuff. So if you think about it, it's called actually video graphics array. So we have an array, and which it makes sense that we have an array because, we are looking in 2D, right? And then, they add multiple dimension, and specifically the third dimension, so you can be able to see the 3D objects, right? So if you look at it carefully, you use this cable, right? All of you have this cable, and we have also other stuff. But, let me give you an example about what is the difference between VGA and HDMI. So majority of the computers now on screens are moving into HDMI and, DVI and display ports and all these things. Those guys are digital interfaces. But VGA is what? Analog interface. Okay, so there is digital interface and there is analog interface. Sounds good? So VGA is the beginning of the revolution of moving to the digital world. So HDMI, mini HDMI, micro HDMI, DVI, display ports, all of those guys are more digitalized, and in a way that, the resolutions will look better, so it look like real. But, VGA is something kind of analog. You move to digital, so the resolution will be a question. Of course, if you look to that, you will find out that, we have a multiple resolution, right? So, sorry, that's something else. So if you think about it, if I would like to talk to the VGA, I have to think about what type of the, what type of the signals I have to poke or, activate or deactivate. So basically, if we are looking to 2 dimensions, we have to look to one signal for the horizontal movements, and the one is for the vertical movements. Okay, so we have horizontal and we have what? Vertical. So if you look to the Vivado, so let me see if I have Vivado open, so I can open Vivado for you. Sorry about that text time, guys. I don't have that much area left. You guys see my Vivado?
Yes, Professor.
Yeah.
Okay. So if I go here in a constraint, I will look into where exactly we can communicate with the VGA. So I go here, buttons, PMODs, PMODs here, accelerators, temperatures, FM. Where's the VGA? VGA. You guys can see VGA. Yeah, here. Did you see that? VGA, right? So this highlighted area are those signals we're gonna use for communication with the VGA, okay? So there are 3 different sets of colors. So, you know that the whatever, pictures or video we are streaming, we are watching is a combination between 3 different colors, right? which is basically RGB, right? So we have the R is standing for red, and the green, and blue. And when you mix between those three guys, you will come out with all different type of the spectrum of colors you can see on the screen, right? So those guys are more AD, like analog to digital, digital to analog to digital converter. So you can elevate and decrease the brightness of the red colors out of the three things, or the green color out of the three things, or blue colors out of the three things, or you can mix between all of them together by using a bunch of counters. So we need counters for working on this. Then the most important part, you have to actually turn on the screen with powering it up with timing, so you will be able to do what? To see, display whatever you're gonna present as a pixels out of the three different colors. Okay? So you are turning on a grid, on array, and then you will start injecting pixels, and by bunch of pixels you will be able to draw a picture. Or when you put pictures and running by another picture, you're gonna do something that's called framing, which is video. Okay, so our mission is to actually generate those two guys, HS, VS. One is horizontal, one is vertical. Then the second question we have in mind, what is the resolutions we are targeting? What are the resolutions we are targeting? So there is a bunch of the resolutions. So basically, if you click on one of those buttons on the screens, it will tell you what is the resolution, right? So if you go ahead like this, sorry about that, and you say here display, nope, here's the resolution, right? So bottom of the resolution here is 800, 600. So the screen I have now, this is kind of modern screen, but there is actually lower than that from the old version Dell I have here in my computer in front of me on the third screen on the side here. So when you are designing the grid, you have to look to the resolution. And when you look to the resolution, you have to look to something which is basically standing for the maximum frequency. And when you look to the maximum frequency, you're not going to run in 100 megahertz. So you need to use also something which is basically the PLL, which is a phase lock loop IP that I showed you for the clock divider, or you can build your own clock divider for meeting the requirement of the screen resolution. So back to the perception here. So what you need to do, basically, you need to turn on signal like this. Did you see the shape of the signal? You're gonna be high for a certain amount of time, and then you will gonna go down here, and then you're gonna go high, and then what you can do, you're gonna go vertically one by one. So you're gonna move one horizontal, horizontal, till the end of the horizontal. Then when the last line of the horizontal happened, the vertical will be 1. Then you will return it back to do horizontal, the whole entire sheet. Then you will return it back to move another vertical. Then you will do another round, then another vertical, then another round, another vertical, until you will cover the whole entire grid, and that's gonna be automated. That means once you will do this, it will do it based on the timing. So the whole entire game is basically what? Counter for the horizontal, counter for the vertical, and of course, some of the conditional boundaries for this. We're gonna be basically, it can be latch, it can be a flip-flop for this running in high frequency. And by this way, you will be able to generate the H and V. When you generate H and V and you connect it to your board without even RGB, guess what you're gonna see? You will see the screen start communicating with you and giving you lines. Okay, I'm not gonna go now in technical too much implementation. I will leave it for the next time, but at least I'm showing you what is this. Okay, now can you see this display time and the display time? Can you see this here, display and display? What is those guys? Those guys are basically the version. So basically, what you need to do here, did you see this 640, 480? Hello?
Yeah.
So those are actually the dimension of the display in horizontal vertical. And those actually coming from the manufacturer. You are not inventing them. So there is a table somewhere here. I can show it to you in Google, our lovely Google. VGA timing table. You see that? Everybody can see it, right? Look, 640, 40, 80, 60 hertz, right? What is the pixel maximum frequency? Going to be 225 megahertz with fraction. So of course, this fraction is going to be really painful for you. PLL will help you with that. Then, you know, all of this, see active video from Porsche, you know, synchronizations, whatever. These numbers you are not inventing from yourself. You have to take it literally. It's coming from the manufacturers. So 640 is the active video. 480 is the active video for the verticals. Then, you know, those, you know, front, whatever you have to put in the consideration. If you are moving in different resolutions, going to be different numbers and so on. So back to this interface. So did you see this front Porsche, sync, whatever, you know, back Porsche, right? Those coming from where? Here. Back Porsche, sync pulse from Porsche for the verticals, and the same thing also for the horizontal and verticals. All of these numbers are gonna be what? Parameters. So you're gonna do them as a what? Parameters. And then you start counting and you will be done. So that guy actually, luckily he made actually an example in front of you for the code and show that, you know, he's making counters, and from there he's actually looking for the dimensions, and from there, you know, he generated the H and V data. And basically this is the analog part that I was talking to you about. So at least now it's draw in your head, what is VGA? What is the expectation? We're gonna play with counters. What is those counters are doing is basically counting this line to line to line counting, and then moving to another line, another line, another line, another line to the end of the button of the screen. Then, you know, you will elevate the vertical one line, then you will turn it back horizontally, then, you know, you will increment second line, and you will do the same thing for horizontal, then you will turn to the last one, and then the last vertical will be initiating back to the horizontal, and you will move forward in infinity loop. Any questions so far? Hello?
No questions.
Okay. So building the code, it's a piece of cake. You know, trust me. I think I have here some code I can show it to you, but, you know, we can work on it later on as well. So where's my code? VGA. So what I was talking to you about, it's basically this one, which I call a driver here. I'm gonna write it next time to you very long, completely, and we're gonna test it together. But, you know, I'm just showing you the concept, okay? So that's actually huge. It's same thing, the same family. So, you know, look, all of the line that I got in information, and I added in front of you here for the 640 times 480, right? Are high refresh rate monitors enabled by faster timings? You can do this, but we have to look to the number in the manual, because also we don't want to go outside the range. So it will be running, but your eyes will not recognize. You know what I mean? Because don't forget, as humans, we are limited by our sensors. So what sensors I'm talking about? Sensors of your ears is limited in a certain bandwidth. Then if you go outside from this way to this way, you will not be able to see to hear anything. Same thing for your eyes, based on something that's called HVS, human visual system in your brain. So you can see up to a certain level. Below that you cannot see. Above that you cannot see. It can you can consider as a kind of noise. Yes.
What was the question? I'm sorry. I think he sent it to you privately.
Somebody messaged me privately. Say, are high refresh rate monitors enabled by the faster timing? Okay. Anyway. So anyway, you put this number, and I just would like to show you what I'm doing. Look, it's just what counter. The old and that trick just counter. I count, then I start the vertical, then I count, and after that I will go ahead to put the boundaries. Like when you're gonna start, when you're gonna end. And then from there you can get what the VC or the HV or whatever, those two signals to be what located. Then I activated the screen. Then I put some context here for what's called for making some straps on the screen, and you will change the size of the straps. You can actually put like a logo, you can put a numbers, you can do whatever you want based on like a BRAM examples, and that will be also covered by the next lecture. If there is no questions, I can show you
actually,
something.
Professor.
Yes, sir.
So all the values that we have for this specific resolution, they're just being applied to these counters?
Yes, I mean, for the timing line, I would like to count from here to here 800. I would like to count from here to there 700 something,
And essentially this is just the enables for all the...
To enable the V and H.
The V and H, right?
Yes,
Which
and then you will connect it to them, then the screen will start communicating with you.
So the V and H takes in, I see the final output for this is just those two values.
I can show you. Look, there is here a clock clear, right? Those two guys, I need them. How I'm gonna activate them using those counter things. Okay. Then those two guys is different story. What is those two guys? Do you remember the VR? The VR, VV, VG. When I said green and color and all of these things.
Yes.
Those are the one, but we don't need them now because I'm gonna communicate them with this called video on, and this video on will be like if you would like to put a picture, logo, whatever, streams, something you have to build by your own self, and that will be a very good for you when you will go into the processor level for the 4305.
Okay.
Okay, because now I can make a finite state machine making the stuff restricted, but then how much finite you can go into a state is called blowing finite state machine. That means your finite state machine will be huge and will be eating the whole entire resources you have on the chip. So in that case, you will need a kind of a behavior of processor, like soft core processor, microblade, and so on. You will communicate with this driver with the processor. Then in a C, you will be start writing commands and pushing arrays. Then you will be able to present it on the screen.
I see. So this driver is only producing us, only giving us that H sync and the V sync.
Just turning in and simplifying, presenting some stuff on it. So conceptually, you will understand what's going on.
I see. But it takes a processor for this to actually digest the data.
Yeah, I mean, unless you like to make it in optimized finite state machine. I mean, I've done it before many times and built games using this without even a processor. But of course, you have to put the time of the development in your priority as well, right? Okay. Anyway, there is other subject I would like to share with you, and this subject is very easy actually to follow. And let me see if I have it in the right place or not, because I have a ton of other stuff. No, that's something else. And that's also something else. And then, you know, that's one second. I have it. Where did I put it? Oh my gosh. You know what? Just go here and I search for PWM. Where is my presentation for the PWM? Where did I put it? Oh, I know where I put it. I'm gonna put also this information to you guys on the what's called Blackboard. Week 13. That's the VGA. This is the PWM. Can you guys see my screen?
Yes, Professor.
Okay, let me actually do something. 1 second, so. What? Oh, kind of like scheiße. Okay. What I can do, I can just go ahead and say share screen, and I can make you look to the big screen, and then I go from there. Can you see the big screen now?
Yes.
Okay, so there is something we are heavily using also on the context of robotics. So if you guys are interested in robotics and control systems, we need to learn how to use this lovely FPGA for controlling movement, like step motors, a wide range of coloring, for instance. And of course, because the board that we have an educational board. So if you guys remember, we have here 2 LED, and those 2 guys are coloring LEDs, right? You guys are aware that we have coloring LEDs on the board?
Yes, the RGB LEDs.
Yes, yes. We have two of them. And these 2 actually are very interesting to use. Okay. So why we need them if you would like to test the PWM is used for. And also you can make it with a gadget like an connected to the PMOD. When you will elevate your voice, the coloring will be brightener. When you are actually talking in a low voice, then you know the brightness will go down and so on. So you can make it dynamically. And that's one of the good actually practice you can do. And you know, it would be awesome if you put it on the GitHub. So you know that will show that the people who are seeking internships, students, to think about hiring you. So PWM stands for.
PJ comes with the microphone. I'm so sorry, I don't mean to interrupt.
What's that?
That PJ comes with the microphone. I did not know.
Yes, there is. No, you can actually connect the microphone for it. It's not actually how it's PMOD.
Oh, I see. So that's a separate component.
Yeah. Oh, you know, you can actually do something. We have accelerometers, so you know you're gonna learn something. It's called SPI. If I have time, I can show it to you as well, because you know what I want. I don't want just like a course and you just take a grade and you leave. You know, I would like also the course will have impact on your life. So the PWM is a pulse width modulation. And see, if you notice, I put it here for 304, but you know, it is for, you know, it's used for the context of the 3300 as well. So the definition is a technique that's, you know, this is just like formulation stuff. So it's a technique that conforms a signal width. So you already have a signal and you would like to increase and decrease the size of the signal. And we did this kind of practice, if you remember, when we played with the clock divider. You guys remember? In the clock divider, we came and say, what is our reference and what is our target? And from there, we start increasing the on and off period of the clock. The difference between here and there, the definition of the clock, the on period and off period, they have to be the same time. And the period of the duty cycle is basically half on, half off, right? So that was the clock divider. But then, you know, in our case for the pulse width modulation, it's not the case that the on will off will be the same. So pretty much you can take it as it's a clock divider, but it's not 100% on and off the same. You understand what I'm saying? Hello?
Yes, so essentially there's a percentage that the signal is on and the percentage that it's off.
Exactly. So same thing, but they made it a new name and they call it pulse width modulation. It makes sense because you don't want to mix between things, right? So generally, a pulse is based on a modulator signal information. And of course, it looks at big words written in the slide, but when you will see now, in the next slide, you will be laughing. So on-off behavior changes the average power of signals. Output signals alternates between on and off within a specific period of time. Same almost definition of the clock. If signal toggle between on and off quicker, the load, then the load will not be affected by toggling because you are communicating with analog devices. So this is the digital part or the digital interface of an analog device. So the motor is analog, but you are communicating, you are controlling using what? Digital. So that's why you need pulse width modulation. And of course, you have to take into consideration how can you do this. So here's a story. Did you see that? So the duty cycle is a measure of the time the modulated signal its high state. Because when it's high, movement will happen. The step motor will start moving. So if you look, for instance, to the draw here or the graph or whatever you can name it, so you will find the step motor will be on. It will start moving. But then, when the off happen, I'm done. I cannot be running. So the motor will be stopping, doing nothing. So how can you reach such a kind of thing? You have to think about it, right? So you have also to think about the frequency in the perspective. So if you look here, switching frequency. So the frequency periodically would like the movement of the motor, for instance, to happen, or the brightness, sharpness, or redness will happen. So we have here an equation, say, switching frequency is the frequency of the rectangle wave of this duty cycle, 1 over the TPM, okay? And then, we need to define some resolution. What resolution? The footstep of moving from the lower to the higher. So you have to, you have to figure out a way to say that, it's a bright by this amount. So what is the movement in digital will be? It's the brightness increased by this amount. So that means how many steps of this will be. So that's actually the resolution. So it's a minimum incremental step of the duty cycle, specified by the number of bits. So now we are involving what? Resolution, number of bits, which is turned to be switches for you, for instance. An example for this, when you say R is equal 7 bits, so that means, the impact will be, the step will be 1 over 128 because we are in a binary form, so going to be 2 power 7. So 1 over 2 power 7 in this case. So if you say that, 8 bits, so you're talking about my footstep going to be 1 over 2 power 8, so that means 1 over 256. How can this circuit will be built? It's a pretty much easy. It's basically like the clock divider. So I have the thing that, in a rectangle in front of you with +1 and flip-flop, it's understandable. This is a counter, right? And this counter, it's going to be represented in how many bits, right? So my counter can be R bits, right? And then I'm going to have a comparator. And this comparator will be comparing between two values, the duty versus the counting. And based on the counting in a less than equation, I will come into the point that I need a boost or a buffer to present the output as a single wire. And the single wire will be the PWM out. And in that case, when I meet the R values, so the counter is R, right? So the counter is presenting a value in a decimal. So that value will be compared with the value in the duty. And then, you'll come into the comparison, on, off, on, off, on, off, based on that. That makes sense? And that's called basic PWM design. So it's not really fancy. It's a kind of basic. So if I want to go into more fancier version, I will go into enhanced version. And in enhanced version, I will start playing with amplitude as well, and the duty cycle in the area you can see in the other side, right? Can you see this?
Question.
Yes, sir.
So does the counter reset to 0 once it, like for example, once it reaches the duty cycle, the max, however you want it high, Then how does it reset for the next cycle? Like for the next.
It's a periodic, right? It will go by itself.
Okay.
It's a counter. You don't touch. Once you reset, leave it running. Okay. Maybe the point that I'm understanding what you're saying is gonna be when you reach the maximum of the counter.
Correct. Yes. What point is a reset itself?
So you have to be sure that the duty is not above the R.
Mm-hmm.
You understand? So the duty should be in the middle of the range of the 0 to R, 2 power R. That makes sense?
Correct. Yeah.
Anyway, so the system frequency is basically 100 megahertz, and that's basically coming from the XADC. You guys agree? Then the PWM resolutions, we call it R, right? So 2 power R, you will get the TPWM. Then, switching frequency, what is the range? It's gonna be the system divided by 2 power R, and from there you can get into the divisor. As you can see, so the desired PWM frequency is basically system frequency divided by the divisor time 2 power R. Okay, I'm giving you theoretical today. So theoretical of the PWM, the theoretical of the VGA. But then what is the practical will be next time. That makes sense? Then that's gonna be the XADC. I would like to know from you guys, are you interested to learn on XADC as well or not? That's like an optional sense. Do you guys like to know more about XADC or not? That's up to you. So who actually in favor of to learn more about XADC if we have time after we finish? Okay. So XADC is an IP. It's an ASIC on the Nexus 4 DDR. And the communication with that, it's coming on the specific PMOD. And you can actually look to your board and you will find there is a PMOD which has under the PMOD is something is called XADC. Can you guys see it? It's on your right hand. So you'll find it as a XADC, right? This specific one is the one will allow you to communicate with the ASIC analog part of the ADC on the board. And we can talk more about this next time because I will show you a system, take a PWM, and you will just map it on the spectrum of the coloring LEDs. Any questions so far? Copy of this will be shared with you. Okay? Sounds good? PWM and VGA. That's actually specifically how can you use the VGA, but I'm going to show it to you next time. Okay? And even the resources of the talk of the XADC with PWM as well. Okay, so now we will move to the next part of the lecture, which is what you guys gonna show me what you already have done with the lab. Sounds good? Any question?
Oh, Professor, is the midterm still on Wednesday?
Gonna be Wednesday.
Okay. Thank you.
So not Wednesday, Monday, we're gonna have a lecture, and this lecture will be about what the practical part about the VGA and PWM. Okay. Then Wednesday, you like guys to focus more on your project, or you would like me to give you another lecture on Wednesday as well? Which way you prefer?
Are you talking about this Wednesday, Professor?
No, not this Wednesday. The next week. So you know how it works since we start this course, right?
Correct. Yeah.
Yeah. So every Wednesday is dedicated for the lab, and one lecture on the XADC. Yes.
What would the next lecture be on if you did give it on Wednesday?
So Monday I will be giving the practice part of the VGA and PWM. Then do you like me to wait for the next Monday to give you the XADC as an extra thing, or do you want me to give it on Wednesday like a short lecture?
Personally, I think Wednesday as a short lecture would be just fine.
Yeah.
Okay. Okay, so majority of you are in favor of this. So next week, Monday will be dedicated for the VGA, PWM. The rest will be dedicated for who? For the XADC or some other crazy project. I can show it to you, like a step motor or whatever, you know, something fun, Then, we'll be done with the course, and then, I will be waiting for you to present on the designated time based on the syllabus for the project. And of course, if you have any questions, I will help you. So I think Christopher and somebody, he asked me about the to assign a project after they think about it, right? What was it, Christopher? Who?
Correct. Yeah, I got your email.
Did you get the email for the bluefish?
I did.
Okay, so you're gonna work on the bluefish. Okay, it's a very easy. It's a very it's a 25-minute practice. Don't worry. Okay. Okay, so now I would like first to thank you guys for attending the course today, and thank you for all efforts you guys are spending, and I hope that you guys are learning something out of this course. This is the most important part for me. For the grade thing, don't worry. For the quiz, I didn't have time. I was really busy with some stuff with NASA, but I will do my best on this weekend for grading the quiz and posting the results. And as I promised you, if you are doing great in the second quiz, the first one will be taken away. But unfortunately, if you are not doing great in the second one, then the 2 grades will be taken into consideration. That makes sense? And same thing for the midterm as well. Okay?
And to clarify, the midterm this coming Wednesday would in fact be on that 2-day period, or have we decided on a 1-day period?
It's gonna be also 1 day, and then there will be like an extra hour for those people outside the United States.
I see. Okay.
But, due to the COVID and all these things, they were stuck in their countries, so it was really hard. Okay. Perfect. So, Group A, stay in the line, and the rest will be out every 5 minutes. A group will be coming, and how it works, right? 50% on the demo, 25% on questions, 25% it will be about the report and how you guys sort it. Okay, I'm gonna stop recording from here, and I'm waiting for the group. Group A. Thank you.